The aluminum sheet arrives at the factory still cold from the foundry, its surface dull and unmarked, waiting to be transformed into something that will carry men into the sky over Europe and the Pacific. This is the Willow Run plant in Michigan, and it is 1943, and the war is devouring aircraft faster than anyone imagined possible. Inside this building, which stretches for more than a mile under one roof, 25,000 workers will take raw metal and turn it into a B-24 Liberator bomber in the time it takes most factories to build a single wing. This is not just manufacturing. This is industrial warfare, and every rivet, every seam, every hydraulic line is a small battle won against the clock and against the enemy 6,000 miles away. The process begins not with assembly, but with procurement. And procurement in wartime is its own kind of survival challenge. The aluminum comes from bauxite mines in Arkansas and Jamaica, where the red earth is crushed and chemically stripped to extract alumina, which is then smelted in massive electric furnaces that consume enough power to light a small city. The electricity comes from dams built specifically for this purpose, because aluminum production requires so much energy that the metal is sometimes called congealed electricity. Each pound of aluminum demands 4 pounds of bauxite and 2 kilowatt-hours of power. The smelters run 24 hours a day, their crucibles glowing orange-white as the molten metal is poured into ingots that weigh 500 pounds each. These ingots are shipped by rail to rolling mills, where they are heated and passed through massive rollers again and again until they become sheets thin enough to form the skin of an aircraft, but strong enough to withstand the stress of flight at 200 miles per hour and 20,000 feet. When the sheets arrive at Willow Run, they are stacked in warehouses organized with military precision. Each sheet is tagged with specifications: alloy type, thickness, temper. The 24 ST aluminum used for the fuselage has been heat-treated and aged to achieve a tensile strength of 64,000 pounds per square inch, which means it can resist tremendous forces without tearing. The workers who handle these sheets wear cotton gloves because the oils from human skin can cause corrosion. And corrosion in an aircraft means structural failure. And structural failure means 10 men falling from the sky in a burning hull. Everything here is connected to life and death in ways that are immediate and unforgiving. The first step in transforming sheet metal into an aircraft component is pattern making. The engineers have already designed every part of the bomber in painstaking detail, translating the aerodynamic requirements into blueprints that specify dimensions down to the thousandth of an inch. From these blueprints, pattern makers create full-scale templates from heavy paper or thin plywood. These templates are laid onto the aluminum sheets, and workers trace around them with scribes, marking the cutting lines. The scribes are sharp enough to leave a visible groove without penetrating too deeply, because every scratch weakens the metal. The marked sheets are then moved to the shear stations, where massive hydraulic shears slice through the aluminum with the sound of tearing thunder. The shears can cut sheets 20 feet long in a single stroke, their blades sharp enough to leave edges that require only minimal finishing. But cutting is just the beginning. The flat sheets must be shaped into curves and angles that will form the three-dimensional structure of the aircraft. This is where the real alchemy happens, in the press shops where metal is bent and formed under pressures that would crush a car. The hydraulic presses are multi-story machines, some exerting forces of 500 tons or more. A flat sheet of aluminum is placed on a die, which is a precisely machined steel form shaped like the interior of the part being made. When the press descends, it forces the aluminum sheet against the die, stretching and compressing the metal until it takes on the die's shape. The metal resists. It wants to return to flatness. The press operator must calculate the exact amount of overbending needed to compensate for springback, the tendency of the metal to partially return to its original shape when the pressure is released. Too little pressure and the part is undersized. Too much and the metal cracks, ruined. The formed parts emerge from the presses as recognizable sections of an aircraft: nose cones, fuselage sections, wing ribs. But they are not yet ready for assembly. Each part must be drilled with hundreds of holes for the rivets that will join it to adjacent parts. The drilling is done with templates that ensure every hole is in exactly the right position. Because if the holes do not align perfectly during assembly, the entire structure will be weakened. The drill operators work with pneumatic tools that shriek and chatter as they bite through the aluminum, creating holes that are countersunk on one side, so the rivet heads will sit flush with the surface, reducing aerodynamic drag. The drill bits must be replaced constantly because aluminum, despite being softer than steel, is abrasive and wears down cutting edges quickly. While the aluminum parts are being shaped and drilled, other workers are preparing the thousands of smaller components that will make the bomber functional. The engine mounts are being cast from magnesium alloy in foundries where the molten metal burns with a white light so bright it can damage unprotected eyes. Magnesium is lighter than aluminum, but more difficult to work with, prone to catching fire if the machining is done carelessly. The machinists who work with it keep buckets of sand nearby, because water will only spread a magnesium fire. The landing gear struts are being forged from steel in drop hammers that shake the ground with each blow, compressing the metal's grain structure to give it the strength to absorb the impact of a 30-ton aircraft hitting the runway at 90 miles per hour. The hydraulic lines are being bent and flared from seamless steel tubing, each bend calculated to avoid kinking, each flare formed to create a leak-proof seal when the fittings are tightened. The electrical system is its own universe of complexity. Miles of wiring are cut, stripped, and bundled by workers who follow wiring diagrams that look like maps of a city's subway system. Each wire is color-coded and tagged, because in the chaos of combat, a pilot cannot waste time tracing circuits to find a malfunction. The wires are routed through the aircraft structure, held in place by clamps that prevent them from chafing against the aluminum skin, because a single worn wire can cause a short circuit, and a short circuit can ignite fuel vapor. And fuel vapor ignition means the aircraft becomes a fireball in midair. The connectors are sealed with rubber boots to keep out moisture, because moisture means corrosion, and corrosion means electrical failure. The assembly line at Willow Run is where all these separate streams of parts converge into a whole. The line moves at a fixed pace, each workstation responsible for a specific set of tasks. The first station is the fuselage jig, a massive steel framework that holds the curved sections of the fuselage in perfect alignment while they are joined together. Workers crawl inside the half-assembled fuselage, working in cramped spaces where they must fit rivets into pre-drilled holes and set them with pneumatic rivet guns. The rivet gun is a brutal tool, hammering with rapid percussive blows that deform the end of the rivet and create a permanent fastener. Each rivet must be set with exactly the right amount of force. Too little, and it remains loose, allowing the joint to flex and eventually fail. Too much, and the aluminum around the hole is damaged, again leading to failure. The riveters work in teams of two. One person holds a bucking bar, a heavy steel weight, against the back side of the rivet, while the other person operates the gun on the front side. The bucking bar absorbs the hammering force and shapes the rivet's tail into a rounded head. It is exhausting work, the pneumatic guns vibrating the workers' hands and arms until they ache, the noise so constant and overwhelming that even with ear protection, many workers suffer permanent hearing loss. As the fuselage moves down the line, it accumulates complexity. The wing spars are bolted into place, massive I-beams of aluminum that run the length of each wing and carry the primary flight loads. The spars are drilled with precision holes at the factory so that the bolts can be inserted and torqued to exact specifications. Under-torque a bolt, and it can work loose from vibration. Over-torque it, and the threads strip. The bolt fails, i.e. the wing separates from the fuselage. The torque wrenches used for this work are calibrated daily, checked against known standards to ensure accuracy. The fuel tanks are installed inside the wings, welded aluminum boxes that must be absolutely leak-proof because fuel leaks in flight mean fire, and fire in an aircraft is almost always fatal. Each tank is pressure tested with compressed air while submerged in water, the inspectors watching for the telltale stream of bubbles that would indicate a flaw in the welds. The engines arrive from other factories, Pratt & Whitney radials that weigh over a ton each and produce 1,200 horsepower. 4 of them will hang from the wings, their weight supported by the engine mounts that were cast from magnesium weeks earlier. Installing an engine is a delicate operation requiring a hoist and a crew of 6 workers who guide the massive assembly into position and secure it with bolts that must be safety wired, a process where thin steel wire is threaded through holes drilled in the bolt heads and twisted tight to prevent the bolts from backing out under vibration. The engine installation crew then connects the fuel lines, the oil lines, the hydraulic lines for the propeller pitch control, and the electrical connections for the magnetos and starter. Each connection is a potential failure point, so each is inspected multiple times by different people before the aircraft is allowed to proceed down the line. The propellers are works of art disguised as machinery. Each blade is carved from a single piece of aluminum alloy. I machined to an airfoil shape that varies from root to tip because the blade travels faster at the tip than at the root, and therefore requires a different angle of attack to generate thrust efficiently. The blades are hollow to save weight, and inside each one is a counterweight and a pitch change mechanism that allows the pilot to adjust the blade angle in flight. In cruise, the blades are set to a shallow angle to maintain speed with minimum engine power. In takeoff, they are set to a steep angle to generate maximum thrust. The mechanism that changes the pitch is hydraulic, driven by engine oil pressure, and it must function reliably at altitudes where the temperature can drop to 60 degrees below zero. The propeller assembly crew balances each propeller on a specialized machine that detects even the smallest imbalance. Because an out-of-balance propeller creates vibrations that can crack engine mounts and fatigue the wing structure. While the mechanical assembly continues, another group of workers is installing the aircraft's interior. The flight deck is being fitted with instruments: the airspeed indicator, the altimeter, the artificial horizon, the fuel gauges, the engine instruments that monitor oil pressure and cylinder head temperature and manifold pressure. Each instrument is connected to sensors elsewhere in the aircraft through copper tubing or electrical wire or mechanical cables. The airspeed indicator, for example, is connected by tubing to a pitot tube on the nose that measures the difference between dynamic pressure and static pressure, a difference that increases with speed. If the pitot tube becomes clogged with ice, the airspeed indicator will give false readings, so the tube is fitted with an electrical heating element to prevent ice formation. The altimeter is connected to a static port, a small hole in the fuselage that samples the ambient air pressure. As the aircraft climbs, the pressure decreases, and the altimeter's internal mechanism translates this pressure decrease into an altitude reading. The instrument installers must ensure that every connection is secure and every line is free of kinks or restrictions, because in combat, a pilot's survival often depends on having accurate information about his altitude and speed. The gun turrets are perhaps the most complex subsystems on the bomber. The B-24 carries 10 50 caliber machine guns mounted in turrets that can be aimed in almost any direction to defend against enemy fighters. The turrets are hydraulically powered, capable of rotating and elevating rapidly enough to track a fighter diving past at 300 miles per hour. The gunner sits in a cramped position, peering through a reflector sight, his hands on controls that move the turret and his thumbs on triggers that fire the guns. The guns themselves are fed by long belts of ammunition that snake through the aircraft's interior, each belt holding hundreds of rounds. The ammunition is a mix of armor-piercing incendiary rounds and tracer rounds, the tracers leaving a visible streak of light that helps the gunner see where his bullets are going. Installing the turrets requires routing hydraulic lines through the aircraft structure without creating interference with other systems. The hydraulic fluid operates at 3,000 pounds per square inch. And a burst line under that pressure can spray fluid across hot engine components and start a fire. Every fitting is torqued and safety wired. Every line is clamped and protected. The oxygen system is critical for high-altitude flight. At 20,000 feet, the air contains only half the oxygen available at sea level, and at 30,000 feet, the available oxygen is less than a third. Without supplemental oxygen, the crew would lose consciousness within minutes. The B-24's oxygen system consists of large bottles of compressed oxygen stored in the fuselage, regulators that control the flow to each crew position, and masks that the crew wear for the duration of the mission. The system must be absolutely leak-free because oxygen leaks create an extreme fire hazard. Oxygen itself does not burn, but it makes everything else burn much more readily. A small spark in an oxygen-rich environment can ignite materials that would not normally burn at all. The installers test every connection with soap solution, watching for bubbles that would indicate a leak, and they route the oxygen lines away from electrical components and anything that could generate heat. As the bomber nears completion, it receives its skin. The aluminum sheets that were cut and formed earlier are now riveted to the underlying framework of stringers and ribs. The skinning crews work from scaffolds, fitting each sheet into place and checking the alignment before drilling the final mounting holes. The sheets overlap slightly at the edges, and these overlaps are sealed with a special compound to prevent moisture from being trapped between the layers, because trapped moisture leads to corrosion. The riveting produces a distinctive skin texture, rows of slightly raised bumps where each rivet head sits. The engineers have calculated that the drag penalty from this texture is acceptable, though later in the war, some aircraft will be designed with flush rivets that produce a smoother surface. The completed aircraft is rolled out of the assembly building and into the testing area. This is not the end of the manufacturing process, but rather a transition to quality control and validation. The first test is a weight and balance check. The aircraft is placed on scales, and its exact weight is measured, along with the location of its center of gravity. If the center of gravity is too far forward, the aircraft will be nose-heavy and difficult to control. If it is too far aft, so the aircraft will be tail-heavy and potentially unstable. Ballast weights are added or removed to bring the center of gravity within acceptable limits. Next comes the functional testing of every system. Mechanics run the engines, checking for leaks and unusual vibrations, and verifying that all gauges read correctly. The hydraulic system is pressurized and inspected for leaks. The electrical system is energized, and every switch, every light, every motor is tested. The flight controls are moved through their full range of motion to ensure there are no binding or interference problems. The landing gear is retracted and extended repeatedly to verify that the mechanism operates smoothly and locks securely in both positions. If the aircraft passes these ground tests, it proceeds to the flight test phase. A test pilot and crew take the aircraft into the air for the first time, running through a series of maneuvers designed to reveal any problems with handling or performance. They test the stall characteristics, the maximum speed, the climb rate, the fuel consumption. They test the turrets and the bomb bay doors and the autopilot. They intentionally put the aircraft into challenging situations to see how it responds. If problems are found, the aircraft returns to the factory for correction. Most aircraft require at least minor adjustments before they are considered ready for combat duty. The final step before the aircraft leaves the factory is preparation for delivery. The interior is cleaned, and any protective coverings are removed. Yet the fuel tanks are topped off, and the aircraft is flown to a modification center where additional equipment is installed depending on the aircraft's assigned mission. Some bombers receive radar for night bombing. Some receive long-range fuel tanks for missions across the Pacific. Some receive specialized navigation equipment for pathfinder duty. After modification, the aircraft is flown to a staging base where it is assigned to a crew and prepared for overseas deployment. From raw aluminum to combat-ready bomber, the entire process takes approximately 63 days at the height of Willow Run's production. At peak output, a completed B-24 rolls off the assembly line every 63 minutes. This is industrial production on a scale that would have been unimaginable before the war, and made possible by the application of scientific management principles and the mobilization of a workforce that includes women, older men, and anyone else who can contribute. The workers understand that their efforts directly impact the war's outcome. Every rivet they set, every wire they connect, every system they test brings the Allies one small step closer to victory. The B-24 Liberator that emerges from this process is not perfect. It is cramped and noisy and cold at altitude. Its hydraulic system is temperamental, and its electrical system is prone to problems. But it is also capable and reliable enough to fly missions deep into enemy territory and return home with its crew alive. It can carry a bomb load of 8,000 pounds over a range of 2,000 miles. It can operate from crude airfields carved out of jungle or desert. And most importantly, it can be produced in numbers large enough to overwhelm the enemy's defenses and air forces. The factory workers who build these bombers rarely see the results of their labor. They do not watch the aircraft take off for their missions or return with battle damage. They do not meet the crews who fly them. But they know, in the same way the Inuit seamstress knows, that their work is the difference between survival and death. The seam they sew or the rivet they set may seem like a small thing, but when a crew is limping home on 2 engines with flak damage to the fuselage and fighters on their tail, that single rivet might be what holds the aircraft together long enough to reach friendly territory. This knowledge drives the workers to maintain standards even when they are exhausted, even when the noise and the pace seem unbearable, because they understand that manufacturing in wartime is not just about production numbers. It is about creating the tools that will allow their sons and brothers and husbands to come home alive. In this sense, the factory workers and the indigenous hunters are not so different. Both are engaged in the essential human struggle to master their environment and create the technologies that make survival possible in a hostile world.